Here in section 1.4, we start using definitions of the trig functions to form what we call trigonometric identities. And being able to work with trigonometric identities is really important throughout trigonometry and also as you get into calculus. First of all, we're going to start with the idea of reciprocals. One thing that we know is that multiplying reciprocals together should always result in a value of 1. So let's take, for example, the number -4/3. If I multiply -4/3 by its reciprocal, I should get +1. And its reciprocal, of course, would be negative. Remember, reciprocals always have the same sign. That would be negative, and then we flip the fraction and we get -3/4. So a negative times a negative gives us a positive. The 4's would cancel, the 3's would cancel, and that would leave us with 1's everywhere. So we do get +1 as we multiply those two reciprocals together. Similarly, we know that sine of an angle times cosecant of an angle, since we're describing the same angle theta here, sine and cosecant are reciprocals of each other, we should also get +1. So let's go back to our definition of sine. Our definition of sine of an angle is y over r, and we're multiplying that times cosecant. The definition of cosecant is r divided by y. So when describing the same angle, we would have the same y value, the same r value, 1's everywhere after we reduce, and then when we multiply across, we would get 1. Since we now know that sine of an angle theta times cosecant of theta, we know that would be equal to 1. Now we can manipulate this what we would call an identity. This is something that would always be true for any angle theta. So let's say that I take this identity and I divide both sides by cosecant theta. Anytime that we use the function name, we always use the input angle. So it's cosecant theta, not just cosecant by itself. Cosecant theta. Cosecant theta divided by itself would be 1. That would leave us with sine theta is equal to, now the cosecants have canceled out, we'd have 1 over cosecant theta. So this is what we would call a reciprocal identity. Now we can also do it the opposite direction. Let's say that I have sine theta times cosecant of theta is equal to 1, and this time I divide both sides by sine theta. Now sine theta would cancel out with sine theta, and I would be left with another, what we would call reciprocal identity. Cosecant theta is equal to 1 over sine theta. So these are what we would call the reciprocal identities because it works with the idea of reciprocals. If I multiply two reciprocals together, we get a +1. If I multiply sine theta times cosecant theta, these are reciprocals of each other, I get a +1. And there are several identities that will follow from manipulating that equation or that identity. And we can see that this would follow through for all of the trig functions, not just for sine and cosecant, but also for cosine and secant. Cosine and secant are also reciprocals of each other, so that we see that we have this reciprocal identity very, very similar to sine and cosecant, and we have the flip of that as well. And then also it works for tangent and cotangent. Tangent theta is equal to 1 over cotangent theta. These are reciprocals of each other. Cotangent theta is equal to 1 over tangent theta. So these are our reciprocal identities. Now we want to use these reciprocal identities to find function values. In example 1, we are asked to find each function value. Find tangent theta, so this is what we were looking for, given that we know that cotangent theta is equal to 4. Here we're describing theta, which we are going to assume is the same angle. And if cotangent is equal to 4, and cotangent and tangent are reciprocals of each other, then we are going to work with the reciprocal identity. Tangent of theta is equal to, we know that that is equal to 1 over cotangent theta using our reciprocal identities, and cotangent theta is equal to 4. So that tells me that tangent theta is equal to 1/4. Here we're asked to find secant theta. Secant theta is equal to, let's see, we're given the information that cosine theta is equal to -2 divided by square root of 20. Secant theta is equal to, well, secant and cosine are reciprocals of each other. So that's 1 over cosine theta. So secant theta is equal to 1 over cosine theta, so that tells me that would be equal to 1 over -2 square root of 20. When I divide by a fraction, we flip that fraction and we multiply it times the top. So that will give me 1 times square root of 20 divided by -2. So that would be negative square root of 20 divided by 2. So this is our secant theta value. However, we do want to simplify and rationalize as much as possible. Square root of 20 can actually be simplified. Square root of 20, let's take that and let's rewrite that. Square root of 20 would be 4 times 5. We want the largest perfect square that divides evenly to 20 in the front, and we know that the square root of 4 is, of course, 2. So we want to simplify any square root that has a perfect square factor underneath it. Now that square root of 4 is written as 2, the 2's are both on the outside and we can cancel those. So we end up with negative square root of 5 divided by 1, but of course that's just negative square root of 5. So secant theta is equal to negative square root of 5. And lastly, we wanted to find cosine theta. If we were given that secant theta is positive 9.8 and so on. Here, this is actually even simpler. Cosine theta would be equal to 1 over secant theta, and of course, we know that secant theta is this decimal value, so that would be 1 divided by 9.8. 0.4251333. All we have to do is put that into our calculator, 1 divided by that value, and then we will have our answer. So cosine theta is equal to, I put that in my calculator, I get 0.101996569. And then, of course, if you were asked to round to a particular decimal point, then you would want to do that. Here we also want to keep in mind that anytime that we're working with reciprocal values, a reciprocal always has the same sign as the original value. So we notice that in part A, cotangent was given to us as a positive value, tangent is also positive. So they are both positive values. In part B, cosine was given to us as a negative value, so we know that when we finish, secant will also be negative. In example C, secant was given to us as a positive value, so its reciprocal cosine will also be a positive value. So reciprocals always have the same sign. Determining the signs of the trigonometric functions of non-quadrantal angles. Going forward, it will be important for you to be able to tell the signs of all of the trig functions given the quadrant of the angle. In quadrant 1, we know that x is positive and y is also positive. So let's write down that. X is positive, y is positive, and remember that r is always considered positive. in every quadrant because r is the distance from one point, our origin point, to a point that we pick on the terminal side. So since r is positive and x is positive and y is positive, then keep in mind that all of my trig functions are formed by the ratios of y divided by r and its reciprocal, x divided by r and secant its reciprocal, and tangent, which is y divided by x and its reciprocal. Since all of these would be positive values, a positive divided by a positive is also a positive. And since reciprocals all have the same sign, sine and cosecant would be positive. Cosine and its reciprocal secant will be positive. Tangent and its cotangent, its reciprocal, would be positive. So all trig functions in quadrant 1 would be positive for any angle, of course, that lays where its terminal side lays in quadrant 1. What about quadrant 2? In quadrant 2, x is negative and y's are still positive. So here, x is negative, y is positive, and r, once again, is always positive. So let's look at sine. Sine would be y divided by r. Sine would be a positive value divided by a positive value. So sine is positive and also its reciprocal, cosecant. What about cosine? Cosine is x divided by r. X here is negative, r is positive, so what does that tell me about cosine? Well, negative divided by positive would be negative, and its reciprocal, secant, would have the same sign in this quadrant. So cosine and secant are negative. What about tangent? Well, tangent is y divided by x. Y is positive, x is negative. A positive divided by a negative is a negative. And the same would be true for its reciprocal. So here in this quadrant, we would say that sine, let's write what's positive here, sine and cosecant are positive. If we remember that sine is positive, then we should also remember that cosecant is positive because they are reciprocals. All right, now let's look in quadrant 3. In quadrant 3, x is negative and y is also negative. So if x is negative and y is negative this time, let's look at all of our trig functions. So sine is y over r. Remember that r is always positive. So y is negative, r is positive. So that tells me that sine will always be negative, because a negative divided by a positive is negative, and so will its reciprocal. So sine and cosecant will both be negative in quadrant 3. X divided by r, x is negative, r is always positive, and negative divided by positive will be negative. So cosine and secant will always be negative in quadrant 3. And let's look finally at tangent. Tangent is y divided by x. Now be careful here, y is negative and x is negative, but a negative divided by a negative gives me a positive value. So tangent and cotangent will both be positive in quadrant 3. If we remember that tangent is positive in quadrant 3, then its reciprocal, cotangent, will also be positive. Lastly, in quadrant 4, x is positive, but y will now be negative. So let's look at our trig functions. Y divided by r. Y is negative. R is always positive, so sine will be positive as well as cosecant. Negative. A negative divided by a positive will be negative. cosine theta, secant theta. Well, cosine is x over r. X this time is positive. R is positive. A positive divided by a positive is positive. So cosine will be positive as well as secant. And lastly, tangent. Tangent is y divided by x. Y is negative, x is positive. A negative divided by a positive will also be negative. So tangent will be negative and cotangent will be negative in quadrant 4. So in quadrant 4, cosine and secant are positive. If we remember that cosine is positive in quadrant 4, then we should remember that its reciprocal, secant, would also have the same sign in that quadrant. Now there are ways to remember this. Sometimes people remember it as all from quadrant 1. All students, so all are positive in quadrant 1. All students, that S would stand for sine, take, the T stands for T in tangent, calculus. So all students take calculus. All means that they're all positive in quadrant 1, and then in quadrant 2, students means sine is positive in quadrant 2. Take means in quadrant 3, tangent would be positive, and calculus stands for cosine. So all students take calculus. That will help you remember which functions are positive in each of the 4 quadrants. Now that we know which trig functions are positive in which quadrants, let's start to work with that idea here in example 2. In example 2, we are asked to identify which quadrant that the angle lays in given the following conditions. Part A, cosine theta less than 0 and sine theta is also less than 0. When we are told that a trig function value is less than 0, then that tells us that that trig function value is considered to be negative. So we are working in a quadrant where cosine is negative and also sine is negative. Well, cosine is positive, we know, in quadrant 4 and also positive in quadrant 1. So for cosine to be negative, we either working in quadrant 2 or we are working in quadrant 3. So these are where cosine is negative. In sine theta, for sine theta to be less than 0, for it to be negative, we are sure that quadrant 1 sine is positive, and in quadrant 2 sine is also positive. So sine is only negative in quadrants 3 and quadrant 4. So which one quadrant are we talking about if both cosine and sine are both negative? That must be describing quadrant 3. So for sine and cosine to both be negative, we must be living in quadrant 3. So the angle theta lives in quadrant 3. In part B, cosine theta is greater than 0, which means that it's positive. Secant theta is also positive, greater than 0. Now cosine and secant are reciprocals of each other. We know that they are both positive in quadrant 1. They have the same signs. In whatever quadrant they live in, they're both positive in quadrant 1, and they are also both positive in quadrant 4. So we could be talking about actually 2 particular quadrants. So we have more than one quadrant which we could be describing. We could be describing quadrant 1 and quadrant 4. So both of those would be would satisfy the conditions for where theta could lie if cosine is positive and also secant is positive. In part C, cotangent theta is less than 0, so we want to find where cotangent is negative, and secant theta is less than 0, so we're talking about where secant is also negative. So where's cotangent negative? We know that cotangent is positive in quadrant 1 and in quadrant 3. So for cotangent to be negative, we're talking about quadrant 2 or quadrant 4. Secant is negative. Let's first describe where do we know that it's positive. Well, we know that secant is positive in quadrant 1, and we know that secant is positive in quadrant 4. So for secant to be negative, we are describing either quadrant 2 or quadrant 3. So which quadrant are we talking about if we must have cotangent being negative and secant being negative at the same time? Well, they would both be negative at the same time in quadrant 2. So in quadrant 2, both of these functions would be negative. Now this time in example 3, I am going to give you the angle that we were talking about, our angle theta, and everything else we've just said theta. We didn't describe what the actual angle was. In these examples, in part 3 here, example 3, I'm going to give you the exact angle, and I'm going to ask you to come up with the signs of all of the trig functions for that given angle. So if angle theta is negative 115 degrees, we first want to know what quadrant our angle lays in. So we want to put our angle in standard position, negative 115 degrees. Well, if I go 90 degrees in the negative direction, that puts me here, and we need to go a little bit more, and that actually puts me into quadrant 3. If I go all the way past into quadrant 2, then of course we will have gone negative 180 degrees plus a little bit more. So we are clearly laying in quadrant 3. Now remember that it's all students take calculus. So in quadrant 3, tangent is positive. So we have positive values for tangent and its reciprocal cotangent. Everything else in quadrant 3 would have a negative value. For 855 degrees, we want to know first, what quadrant does the angle lay in? Let's use our shortcut. We talked about 855 degrees. Let's divide that by 360 degrees. That way we will know how many complete rotations that we have. So 855 degrees divided by 360, that gives me 2.375. So I have two complete rotations. So 855 degrees minus 2 complete rotations, 360 degrees. That would be 855 minus 720. And that gives me 135 degrees. So we know that 855 degrees is coterminal to 135 degrees. It's a positive angle in standard position. So we know we want to go 1 complete rotation, 2 complete rotation, and then we want to go 135 degrees more past those 2 complete rotations. That puts me into quadrant 2. All students take calculus. So that tells me that in quadrant 2, sine is positive along with its reciprocal. So sine is positive and its reciprocal cosecant is also positive. All of the other trig functions will be negative in quadrant 2. The Pythagorean identities come from the Pythagorean theorem. If we have a right triangle, and we've discussed this when we formed our definitions of our trig functions, the side that is the hypotenuse would be called our r. The sides of the triangle that are not the hypotenuse, we would call those x and y. So that would lead us to the Pythagorean theorem, being y squared plus x squared equals the hypotenuse r squared. Now if I take this Pythagorean theorem, which would be true for this right triangle, and treat this just like I would treat an equation. For example, we know that whatever I do to one side, I have to do the same thing to the other side. Let's take everything in this Pythagorean theorem, everything in this equation, and divide by r squared. As long as I do the same thing to everything, the equation, the theorem will hold true. So when I divide, well, y squared divided by r squared, that is the same thing as sine squared of our angle theta. Y divided by r would be sine, and y squared divided by r squared would be sine squared. Plus, x divided by r would be cosine, and since they're both squared, that would be cosine squared of our angle theta, is equal to r squared divided by r squared would be 1. So our Pythagorean identities come from the Pythagorean theorem. Now we do want to have these Pythagorean identities memorized. However, if you can remember the Pythagorean theorem and divide everything through by r squared, you don't necessarily have to memorize it, but you can develop it using this technique. And this would hold true for any angle theta, as long as theta is describing the same angle. We also want to be familiar with any form of this. Treating this once again as an equation, I should be able to take sine squared and subtract it from both sides. If I do that, we will end up with cosine squared theta equals 1 minus sine squared theta. And this would be an equivalent form of that identity. So we should be able to know the basic form of the identity and then be able to rearrange it by subtracting or adding or doing anything to both sides. We should be able to come up with an equivalent form of that identity. What about tangent squared theta plus 1 is equal to secant squared theta? How do we get that Pythagorean identity? Well, let's take our Pythagorean theorem again. Y squared plus x squared equals r squared. And this time, let's go through and divide everything through by x squared. Alright, so if I do that, y divided by x is tangent, and they're both squared, so that would be tangent squared theta. Plus, x squared divided by itself would be 1, is equal to r divided by x is secant, and since they're both squared, that would be secant squared theta. So this would be one form of the tangent secant Pythagorean identity. And once again, I should be able to rearrange this if I subtract 1 from both sides, or if I subtract tangent squared theta from both sides. Whatever I would want to do to both sides of this equation, I would come up with a different form of that Pythagorean identity. But it's an equivalent form. Okay, lastly, let's take that same Pythagorean theorem, and this time, the only thing that we haven't done, we haven't divided everything through by y squared. So let's do y squared, y squared, y squared. If I divide everything through by y squared, y divided by itself would be 1, plus x divided by y would be cotangent, that's cotangent squared, is equal to, and then r divided by y would be cosecant, and that would be cosecant squared theta. So this is where we get our Pythagorean identities, and this is why we call them the Pythagorean identities because they come from the Pythagorean theorem and our trig function definitions. Now we will look at the quotient identities. The quotient identities are something that we should have memorized, but once again we will see the logic behind them so that we don't necessarily have to memorize them. Sine divided by cosine is equal to tangent. Sine theta divided by cosine theta is equal to tangent theta. So when we are talking about theta, we're describing the exact same angle for all of them. Cosine theta divided by sine theta is equal to cotangent theta. You notice that sine over cosine is the reciprocal of cosine over sine, and we're talking about what we're describing is tangent and cotangent, which are reciprocal functions. So why is sine divided by cosine equal to tangent theta? Well, remember that sine is y divided by r, and the cosine definition is x divided by r. So in a sense what we are doing is we are dividing two fractions. Sine divided by cosine, and when we divide two fractions we flip the bottom fraction. Let's keep that in the same color. So our top fraction would stay the same and we would multiply by the bottom fraction, which we would flip. So that we would be multiplying by r over x. And our r's would cancel and we would be left with y divided by x. And y divided by x is the description of tangent theta. So if I start with sine divided by cosine, if I use those trig function definitions, we can actually reduce to come up with our tangent y over x. So these will be equivalents or identities. Sine divided by cosine will give us tangent. We can do the same thing for cosine divided by sine to show that it gives us cotangent. Cosine is x divided by r divided by sine, which is y divided by r. We will keep the top equation or top fraction the same, and we will multiply by the flipped y over r. We multiply by r divided by y. So we multiply by the reciprocal, and then we can reduce. Our r's cancel, and this time we're left with x divided by y. And x divided by y is cotangent of the angle theta. So we should be able to go back and forth between these different ways of writing cotangent. Cotangent theta is equal to cosine over sine, or if I give you cosine divided by sine, you should be able to recognize that that would give me cotangent. Now that we know several identities, let's use those identities to find function values that we do not know. In example 4, we are asked to find sine theta, given that cosine theta is equal to 4 over 5, and we know that theta is in quadrant 4. So we are asked to find sine theta, and we know that we are in quadrant 4. What is the sign of sine theta if we are in quadrant 4? Well, sine is negative in quadrant 4. So I will go ahead and put my negative sign there so I do not forget to remember that sine is negative in quadrant 4. Now how do I get from sine to cosine? Using identities. So we're asked to use identities to do this. Well, our Pythagorean identity will help us here. Sine plus cosine. So sine squared theta plus cosine squared theta is equal to 1. So this is our Pythagorean identity that relates sine values to cosine values. So we will use this identity to determine what sine is from cosine. So we don't know what sine is, so we'll see that as sine squared theta plus cosine we know is 4 over 5. So 4 divided by 5, and we need to square that. And now we have an equation that we can solve for sine. So sine squared theta plus, and we will square 4 over 5. That would be 16 over 25. is equal to 1. Now we can subtract 16 over 25 from both sides of our equation. And we know that when we subtract, we do need to have a common denominator. If I was to write 1 with a denominator of 25, of course that would be 25 over 25. So now we have that sine squared theta is equal to 25 minus 16 would be 9. Keep our same denominator. And the last thing that we want to do is to take the square root of both sides. Now remember that when you take the square root of both sides of an equation, we always want to include our plus and our minus. So the square root of sine squared would be sine. Sine is either equal to plus or minus, and the square root of 9 would be 3, and the square root of 25 would be 5. So it's either plus or minus 3 over 5, and we said that we are working in quadrant 4, so we know that it will be negative 3 over 5. In example 5, we are asked to find tangent theta given that sine theta is equal to a positive 1/2 and theta is in quadrant 2. So we want to find tangent theta, and we are told that theta, our angle, is in quadrant 2. If our angle is in quadrant 2, we know that sine is positive in quadrant 2, but tangent will be negative in quadrant 2. So let's go ahead and put our negative sign as part of our answer so we don't forget that part. Now, in order for us to get from tangent to sine, we will use our quotient identity. Tangent theta is equal to sine theta divided by cosine theta. Now we know that sine theta is positive 1/2, but we do not know what cosine theta is. So we cannot directly solve for tangent theta with our quotient identity. We will have to figure out what cosine theta is first. Once we know what cosine theta is, then we can simplify this expression. In order for us to get cosine theta, we know sine. What identity relates sine and cosine? Well, that will have to be our Pythagorean identity. Sine squared theta plus cosine squared theta is equal to 1. Sine squared theta, well, we know that sine is 1/2. We'll square that. Plus cosine squared theta is equal to 1. 1/2 squared would be 1 squared, and then 2 squared would be 4. We will have to solve for cosine squared theta, so we will subtract 1/4 from both sides. Now I know that cosine squared theta is equal to 4 over 4 would be the way that we would rewrite 1, so that we have a common denominator with negative 1/4, and that gives us a positive 3/4, and then take the square root of both sides. That leaves us with cosine theta is equal to plus or minus, and we're going to simplify this, the square root of the top divided by the square root of the bottom. The square root of 4 would be 2. Now we are working in quadrant 2, and in quadrant 2, cosine is negative. So now we know that tangent theta is equal to 1/2 divided by our cosine value, which is negative, square root of 3 over 2. We want to simplify our expression. We have 1/2 times, we will flip the bottom fraction, so that would be a negative 2 divided by square root of 3. Cancel out our common factors of 2. So now we have negative 1 divided by the square root of 3. So our tangent value is negative 1 divided by the square root of 3. Before we say this is our final answer, we want to get rid of that square root that's in our denominator. So we will multiply the top and the bottom by the square root of 3. So our final answer will be tangent theta is equal to negative square root of 3 all over 3. And that is what we knew that tangent theta would be negative, and so this is a reasonable solution. So tangent theta is equal to negative square root of 3 over 3. Here in example 6, we are asked to find the values of the 5 remaining trigonometric functions for each angle theta. So for part A, sine theta is equal to the square root of 2 divided by 6, and we are told that cosine theta is less than 0. Remember that cosine theta less than 0, meaning that cosine is negative, and that will help us to determine what quadrant that we are located in. We are told that sine is positive square root of 2 over 6, so sine is positive. We want to find which quadrant has sine positive and cosine negative. Well, sine is positive in quadrants 1 and in quadrants 2. Cosine is negative in quadrants 2 and in quadrants 3. So which quadrant has both sine positive and cosine negative at the same time? That is quadrant 2. That also tells us the signs of all of our trig function values. Cosine is negative. Tangent, because we're located in quadrant 2, tangent is also negative. Cotangent is negative. Secant is negative, and cosecant will be positive. Now that we know the signs of all of our trig function values, let's go ahead and find the actual numeric values. We know that sine is y over r. So our y value would be square root of 2 for the top of our fraction, that's our y. The bottom value would be 6, that's our r. What we are left to find so that we can form our trig function values would be what is x. Let's use our Pythagorean theorem. We know that it's x squared plus y squared is equal to r squared. And let's plug in our values that we don't know, and that we know. X squared, we don't know that, so we'll leave it as x squared, plus y squared. Our y is the square root of 2. We will square that. And then 6 is our r value, and we will square that. So we have x squared plus the square root of 2 squared, that would be 2. 6 squared would be 36. If I subtract 2 from both sides, we find that x squared is equal to 34, and the square root of x, when we do that, we end up with plus or minus the square root of 34. Now, is it plus or is it minus? Well, we are living in quadrant 2, and in quadrant 2, x is negative. So we know that x is equal to negative square root of 34. Now that we know that x is equal to negative square root of 34, and we know the y value and we know the r value, now we can actually form the values of all of our trig functions. We already know the signs of each one of them, and now we're just looking for the number that goes behind the sign. So cosine is x divided by r. The x value is square root of 34, and the r is 6. So cosine theta is equal to negative square root of 34 divided by 6. Tangent theta, well, that is y divided by x. Our y value is the square root of 2. and our x value is the square root of 34. Now we need to simplify this and rationalize our answer as much as possible. When we go to simplify, square root of 2 on top, 34 can be written as the square root of 2 times the square root of 2 goes into 34. How many times? We have 17 times. On the top we have the square root of 2, and on the bottom we have the square root of 2, so we can cancel out those common factors of the square root of 2. And that leaves us with 1 divided by the square root of 17. So we have simplified, but we need to rationalize. So I'm going to multiply the top and the bottom by the square root of 17 to get that radical out of our denominator. So our final answer will be negative square root of 17 divided by 17. So we want to simplify, get rid of any common factors, and then we want to rationalize. We want to make sure that we don't have any square roots left in our denominator. Cotangent is the opposite, that is x divided by y. And x would be the square root of 34. And our y value is the square root of 2. We're going to do the same thing just in the opposite direction. We're going to simplify. That would be square root of 2 times the square root of 17. So we can rewrite square root of 34. And then on the bottom we have the square root of 2. And our square roots of 2 can cancel. Those are common factors. We end up with 1 as our denominator, so our final answer is really negative square root of 17, and we don't need the divided by 1 part. Secant is r divided by x. R divided by x, so r was 6, and x is the square root of 34. And once again, we need to simplify and rationalize. So we're going to multiply top and the bottom by the square root of 34. And that gives 6 times the square root of 34 all over 34. And now 6 and 34 have a common factor of 2. So we will cancel out a common factor of 2. That leaves us with 3 on the top and 17 on the bottom. And it was negative to begin with, so we end up with negative 3 square root of 34, all of that divided by 17. And the last value we're looking for is cosecant. Cosecant is r divided by y. Our r value is 6, and the y value is the square root of 2. So we need to rationalize and simplify as much as we can. Let's multiply top and the bottom by the square root of 2. We end up with 6 times the square root of 2 all over 2. And once again, 2 and 6 have a common factor. 2 goes into 2 once. 2 goes into 6 3 times, so we end up with a positive 3 times the square root of 2. So we have found our cosine value, our tangent value, cotangent value, secant value, and our cosecant value. You want to make sure that you're careful to simplify and rationalize your fractions. If cosine theta is equal to negative square root of 3 divided by 2, and theta is in quadrant 3, now we want to determine sine, tangent, cotangent, secant, and cosecant of the angle theta. So let's begin by knowing that theta is in quadrant 3. If theta is in quadrant 3, cosine is negative, and so is its reciprocal secant. What is positive? Tangent is positive in quadrant 3, and so is its reciprocal cotangent. Sine is negative, and cosecant is negative. So we know all of the signs of all of our trig functions because of the fact the angle is in quadrant 3. Now we want to know the numeric value of them. And to determine that, we need to know what x is, we need to know what y is, and what r is. X is, well, cosine is x over r, so x is negative square root of 3. R is always positive, so r is that positive 2. We need to determine the value of y. So we'll go back to our Pythagorean theorem. X squared plus y squared is equal to r squared. X squared, negative square root of 3 squared, plus y squared is equal to 2 squared. Square root of 3 squared would be 3. 2 squared is 4. We will subtract 3 from both sides. Y squared is a positive 1. And taking the square root of both sides, we get that y is equal to plus or minus 1. So is it plus or minus? Well, we are in quadrant 3, and y is negative in quadrant 3. So we get y is equal to negative 1. Now let's figure out the values of all of our trig functions. Sine is y over r, so the y value is minus 1, or just 1. We already have the sign there. 1 divided by, our r value is 2, so sine is equal to a negative 1/2. Tangent is y over x. Now notice that we said tangent was positive, and that's because y is negative and x is negative. A negative divided by negative gives us that positive. So we have y divided by x, and we get positive 1 divided by the square root of 3. We want to rationalize, multiply top and the bottom by the square root of 3, and we get positive square root of 3 divided by 3. Cotangent is x over y, and once again, cotangent is positive, and when we go back, we see that x and y are both negative, and when we form a fraction of them, we get a positive value. So our x was square root of 3, our y is 1, negative divided by negative gives us that positive cotangent value. So we get positive square root of 3. Secant is r divided by x. R is 2. X was negative square root of 3, but we already have the sign there, so we just need the number. And we need to rationalize, multiply top and the bottom by the square root of 3, and we get negative 2 square root of 3 all over 3. And lastly, we have cosecant, which is r divided by y. Our r value is 2, and the y value is 1. And we already know that it was negative, so negative 2 is our cosecant value. Now we want to discuss the range values of the 6 trig functions. The range values of the functions are the same thing as the output values of the functions. For sine and cosine, if we are looking at the range values on a number line, the output values of the function would be as small, could be as small as negative 1, go all the way to 1, and the largest value that sine and cosine could take on as an output value would be positive 1. We want to discuss why this would be. When we are looking at our x, y, and r as the sides of a right triangle. R, it would be the hypotenuse. And the hypotenuse, if you remember, would be the longest side of our triangle. If r is always the longest, then if I was looking at the relationship between r and y, r would always have to be larger than y. Or the sides could be equal. But r could not be smaller than y if r represents the hypotenuse of this right triangle. So r must be either larger than y or it could be equal to y. If I look at this as it corresponds to sine, sine is y over r. If y is always smaller, and r would either be larger or equal, well, if they are equal, that would be 1. And if y is the opposite sign, if y is negative, then we would have negative 1. So we could see that if y and r are equal to each other, with y being positive, I would get a positive 1. If y is negative, I would get a negative 1. But if y is smaller than r, let's look at an example like 3/4 or 4/5. If y, the top value, must be smaller and r must be larger, notice that these values would all be less than 1. So we can see how we could pick up values in between 1 and -1. We could see how we could pick up values that are less than 1. But why is -1 at the bottom here? Well, if let's say that y is negative. If y is negative, then let's say that we have a -3 and a -4. Well, these values here would both be larger than -1. So if y is negative, then I would have to be larger than -1. So the smallest value that I could have would be -1. The largest value I would have is +1, and anything in between could potentially be a value for sine. So sine has to be something between -1 and +1 because of the fact that y is always smaller and y is on top for the sine function. The same thing would be true for cosine, because x is also a leg of our triangle. X and y both excuse me, x and y both must be smaller than r. And if x is very, very similar to y here, then the same must be true for cosine. Since x and y are both smaller than r, then the relationship for sine and cosine, the relationship would have to be the same. So cosine and sine are both between -1 and 1. What about cosecant and secant? Let's pick a value out for sine. Let's say that sine, and we have to pick a value that comes from -1 to 1. Let's say that sine is equal to a +1/2. Then the cosecant value would have to be the reciprocal of that. So if I pick a point that exists between -1 and 1 for sine, cosecant would be the reciprocal of that. And you notice that cosecant isn't going to be larger than 1. When I flip a fraction, we get something that is larger than 1 here. So if I flip a fraction that's smaller than 1, we get a fraction that is larger than 1. If sine is equal to, let's say, a -3/4, -3/4 would be in between -1 and 1. Then cosecant, when I flip that fraction, would be a -4/3. Both of these, this is larger than 1, and this value here is less than -1. So for cosecant and for secant, the values of that would have to take on the opposite values of sine and cosine. In other words, starting at -1 and going toward the left, and starting at +1 and going toward the right. So if sine and cosine are in between -1 and 1, then cosecant and secant would have to be either smaller than -1 or equal to -1, or larger than +1 or equal to +1. So the reciprocal values do exactly the opposite as far as their outputs go. So that's why we get this in interval notation. We have -infinity all the way to -1, and then we union that, or we skip over everything between -1 and 1, and then we pick up again from 1 to positive infinity for secant and for cosecant. Now when it comes to discussing the range of tangent and cotangent, tangent is y divided by x, and cotangent is x divided by y. Now, this time we do not have a restriction on which one can be larger and which one can be smaller. X and y are the legs of a triangle, and the only restriction we had for the triangle was that r had to be the largest number, or the largest side of that triangle. X and y can have any sort of relationship with each other. X and y could be equal to each other. Y could be less than x, or y could be greater than x. We also never had a restriction that said that x and y cannot be 0. If y is equal to x, so let's focus on tangent here. If y and x are equal to each other, so say for example 3 divided by 3, then tangent could be 1. If y is less than x, so the top number is smaller, then we could have something that's less than 1. And we could also say that y is negative. So let's say that y is -2. Well, then now we are actually greater than -1. Also, we have y could be larger, so we could have something like 4/3, which is greater than 1. We could also have -4/3, which is less than -1. So we really have all of these possible values for what could happen with x and with y. Also, let's say that y is 0. If y is 0, then we could have 0, let's say, divided by an x value of, let's say, -4. Then we could actually take on a value of 0 as well. We could have all sorts of possibilities for how x and y can relate to each other. So as we start to put together all of these different scenarios, we can see that really x and y, when I form a fraction of these two values that could be any two values and have any sort of relationship, that we could really pick up anything that's less than 1, greater than 1. We could even pick up values of 0. So we actually end up picking up the entire number line for tangent and also for cotangent. If tangent could take on any value, then the reciprocal of that would also take on any value. So tangent and cotangent, with all the possibilities for x and y and how they relate to each other, the output values are unrestricted. So anything from my number line from -infinity all the way to positive infinity could represent the output values for tangent and for cotangent. In example 7, we want to use what we just discussed about the range values of functions to decide whether or not each statement is possible or impossible for some angle theta. So for part A, we want to know, is it possible for sine theta to equal to 3? And the answer for this would be that it is not possible. And the reason why it's not possible is that sine must be in between -1 and 1. Here, sine is equal to positive 3, and that is not possible for sine to be greater than 1. It has to be less than or equal to a positive 1. So what about cosine theta is equal to negative 0.96? Is that possible? And the answer for this would be yes, this is possible. This is possible because cosine values must become in between negative 1 and positive 1, and 0.96, negative 0.96 would be right before negative 1. So it is a little bit larger there than a negative 1. So that would be possible for cosine value to take on that value. Cosecant theta equal to 100. Is this possible or not possible? And the answer for this would be possible. That is possible because cosecant theta must be greater than or equal to 1, or cosecant theta can be less than or equal to negative 1. And here we see that this satisfies the first requirement, cosecant theta being greater than 1. So that is possible for cosecant theta to equal to a positive 100. Is it possible for cosine theta to equal negative 2 and for secant theta to be equal to a negative 1/2? Well, let's first check here. Cosine has to be larger than negative 1 or smaller than positive 1. So this right here is not possible. So the answer for part D there would be not possible. Is it possible for cosecant theta to be negative 2 and for sine theta to be a negative 1/2? So let's check cosecant. Cosecant has to either be larger than positive 1 or cosecant can be less than negative 1. So this satisfies the second requirement where cosecant is less than negative 1. So that is possible. It is possible for cosecant to be negative 2 because that is smaller than negative 1. Let's check the next one. We see that we're given the reciprocal sine is also negative, so the fact that they're both negative, that's a good sign. And the reciprocal of negative 2 would be a negative 1/2. And let's make sure that sine is in the allowable values. The sine values have to be in between negative 1